Let's start recording. Okay, so first thing is F equals MA 2016 review. Okay, so yeah, anything?
Yeah, 19, 17.
Oh yeah, Lewis, I saw you did the thing as well. So if you have any problems that you found particularly confusing.
I don't know. I did it on a time limit. I didn't go past the time limit on purpose, so I didn't really focus on necessarily what was confusing. I just kind of went through it and did as much as I could.
Yeah, you're supposed to do it on a time limit. So
yeah, but
Yeah,
I didn't really
same.
like I didn't see what was hard and what was. I just kind of skipped.
okay,
through.
like, do you want to go through it right now to check like?
Sure, I have my work somewhere around here. One moment, I'll see where I went wrong, or see like the stuff I had trouble with.
Yeah, take like 2 minutes to find like which things.
Yeah, I'll need a minute if I'm gonna find what I missed and what I worked on.
Do you have the answers I submitted?
Do I have your answers? I do.
Okay, can you send me so I can check which ones I did? Huh?
Send you your answers?
Yeah, or just tell me which ones I didn't do.
You didn't do.
I didn't do most of them.
I guessed on some of them as if because that's what I do on the test, wouldn't I? So
yeah, that's fine.
That's why I'm trying to find my original work. I'll be right back.
So, read Jamil. Okay, the ones you did not do?
Oh no. We should start with number 9 because that's the first one that like really 8 and 9, those are the first ones that started tripping me up.
All right, let me just take a look. Uh, 8 and 9. Okay, so 8 actually focuses on the derivation of Kepler's laws, which we did some of, but not all. Okay. All right. And 9. Okay. Okay, yeah, sure. Anything else?
Should I buy a tutor?
Should I buy a tutor?
Or like get one?
I don't know. I think you like practicing on your own and reading the solutions and doing a lot of problems, I think suffices most of the time. I don't know. Do what you think you need. Yeah, Lewis, you wanted to say something?
Oh, I'm sorry, that was an accident. Something played, but yeah, for some reason I had an easier time with like the derivations, I think, later on, like the more intricate solutions. And then I like cracked on like some of the easier like kinematic stuff for some reason.
That
Really
happens to
weird.
the best of us. It's fine though. Just with more practice, you'll make less mistakes on like easier problems. All right, so let's just focus on these four. All right, for now. Okay, number 8. Kepler's law state that, and it lists Kepler's laws, right? So orbits of planets are elliptical with one focus at the sun to a line connecting the sun and a planet sweeps out equal areas and equal times. And 30, the square of the period of a planet's orbit is proportional to the cube of its semi-major axis. Okay, so remind me, like, which ones did we derive? So which of the 3 Kepler's laws did we derive? So 1 is ellipse.
2 and 3.
2 is so like
Equal areas.
areas in equal times, equal areas in equal times, and 3 is t squared is equal to a cubed, right? Okay, so we didn't derive 1, and we're not actually going to worry about that because the derivation is like really hard, and I don't think they're actually expecting you to know it. So like anything involving the derivation of 1, probably not the right answer, right? But then, so how did we derive 2? Let's think about that. So like, what were the general steps we took to derive 2? Equal areas and equal times. Anyone? Draw an ellipse. All right. I mean, I don't want the exact thing with all the technical details. I just want like an overall, because this is a theory question more than a computational question, right? So like, okay, I drew an ellipse. Now what? Where did everyone go? Wait, are you guys not seeing the ellipse I drew? Oh my God. No, I'm not taking that right now. Okay, so yeah, what is the, yeah, cool, thank you. So what are the general steps that we took in deriving the second law? Okay, you draw 2 points d theta apart, right? Okay. So then this is the sun, right? And then I drew 2 points that were d theta apart. I said that, yeah, and then I use sine area, right? So R, and then this is like, this is your dA, right? So dA equals to like half r squared d theta, right? And then we said that, and then we said and this takes place in a time like dt, right? So then dA dt is equal to half r squared d theta d theta dt equals to like half equals to half r squared omega, right? Yeah. And then why is this constant? So dA dt is constant because answer qualitative. First and second laws needed to be an ellipse. With different governing equations, the path would be different. Oh, I wouldn't actually say that's true. You know what? All right, I'll derive the ellipse law in office hours because that actually takes a long time. But like, you know, in deriving like the ellipse law, you have to prove that it's a closed path and then like it's not some weird other shape, right? Okay, so why was dA dt constant? Because 1 over r squared is proportional to omega because of gravity. What exactly does that mean? Okay, so let's consider something, right? So we said that, was this what I described during? Well, okay. So the reason why like we said that this was constant is because, so what does r omega give us? Right? What does r omega give us? R omega gives us like V, right? Huh?
Sorry.
All right. So basically the solution to this problem lies in the fact that in laws 1 and 3, right? Okay, you know what? I don't think I can do this problem without actually showing the derivation of the ellipse law. So we'll ignore 1 for now. All right. But the point is 2 will remain true because like none of this actually like relies on the fact that the force of gravitation is equal to like g m1 m2 over r squared, right? If you think about this derivation, like it doesn't rely on the fact that the force of gravity is equal to this, but instead it relies on, you know, like this little triangle trick that I showed you, right? And then the fact that, you know, it's still going to sweep out equal areas and equal times because, you know, we have like the same formula for a triangle regardless of what force pulls them in, right? But then if you think about 3, all right, how did we derive 3? So the way we derived 3 was, yeah, how did we derive 3? Did we derive 3? No, we didn't. Well, okay, the derivation of 3 relies on the fact that angular momentum is conserved, right? And like the reason why angular momentum is conserved is because of like, no. The derivation of 3 relies on inverse square, actually. I'm sorry this is so messy because I don't recall what I said and what I didn't. Do they use test bank? I don't know. Okay, I'll derive 1 and 3 if you come to office hours on Saturday. Okay, so Saturday 4:30, I will derive laws 1 and 3 because these actually seem to be important for this question. But the derivation of these two rely on the inverse square law, while number 2 just relies on like the triangle, right? So then therefore 2 is conserved because it doesn't matter what inverse square is. But then 1 and 3 are not going to hold because it relies on the inverse square law. I'm sorry that was a bit messy, but that's just what it is for now. Any questions? Yeah, kind of a tough theory problem for number 8. All right, let's move on. Number 9. Let's see. Small bead is placed on the top. Oh yeah, by the way, the answer was like B, which is just 2. E for 9. Yeah, it's E for 9. We have this thing, right? It starts sliding. Find the speed v at which the bead leaves the square. Okay. Oh, it's actually on top. All right, so this is a classic conservation of energy problem. All right, so on top of the sphere, what is the energy of the bead? I don't know. They put like classic problems sometimes. They put like the 2 boxes sliding problem as well at one point. It depends on 0. Yeah, okay, so where do you want 0 to be? 0 at the center? Sure, I'll put 0 at the center. Right, so then the total energy here is going to be, and let's just say this is H, right? So then total energy here is going to be mgh. Okay, and then the only force that's acting on, there's no like, there's no like friction acting on it, right? So then therefore, since all the work that's done on it is by gravity, which is conservative, we know that energy is conserved, right? So then the energy is going to stay at mgh. And now when the bead slides off the sphere, right, which is at some intermediate point. So let's just call like, this angle should be V such that the centrifugal force matches the inward force of gravity. Yeah, that's right. Theta equals 0? No, theta equals 0 it's resting on top of the ball. That doesn't make too much sense, right? So in order for it to be like actually sliding on the ball, it needs to have centripetal force, right? Because it's going through circular motion around like the ball. So then therefore, if I have like this force right here that's pointing inwards, then this is equal to, this is equal to v squared over r, right? But then the only force that could be pushing it inwards into the circle is the part of the gravitational force, that points inwards, right? So then if I draw a thing here. This is like mg, right? So this is going to be theta, and this is also going to be like theta, right? Is that right? Yeah, I think that's right. Okay, so then that means, the inwards force is going to be mg times cosine of theta, right? Okay, but then when the gravitational, so then an object slips when its normal force is 0, right? So slip normal equals 0. And this happens when the centripetal force is equal to the force inwards. This happens when the centripetal force is equal to the force inwards. Because like when all the force inwards is dedicated to keeping the block, yeah, I think it does. It should. We're supposed to treat it like the Earth. No, because we don't treat it like the Earth because gravity still acts like downwards. Right? Yeah, it's just a circle. So that means like whatever the velocity is, right? We have v squared over r, right, is equal to, or mv squared over r is equal to mg times cosine of theta, right? Because at this point, there's no extra force that is actually supplied onto the bead by gravity other than the one that's required to keep it running in a circle, right? So therefore, the circle is actually not providing any normal force to the bead. Okay, so, and then when there's no normal force, then it's going to slip. So we have mv squared over r is equal to mg times cosine of theta, right? Okay, so now I'm going to remove this, right, so far? Yeah. I'm going to call like the radius r, right? So we can remove this, we can remove this, and then we have r equals to d over 2. How you know that? Yes, in circle, the radius, the diameter is twice the radius. Okay, so now we have v squared is equal to r times g sine theta, right? Ooh, did I stuck myself somewhere? Okay, but keep in mind, like this energy is also the energy accumulated when like the block is lowered some height, right? So I'm not going to define it.
Should be g cosine theta, Alvin. You
Hmm?
flipped it.
Cosine?
When you multiply by r, right? V squared over r equals g cosine theta, right?
Yeah, okay. I'm actually going to call, this diagram's getting cramped. I'm actually going to call like this point 0, right? Not the point, not the center. Like, I'm actually going to call this point, this distance h, right? So then we have the potential energy that's lost, which is mgh. So now this is equal to the kinetic energy that is gained, right? So then this is equal to like half mv squared. Just right so far?
What are we solving for?
We are solving for the velocity of the bead. Okay, how can the zero
In
be
terms of
separated?
what?
No, I'm saying the zero is the height at which the bead leaves. All
Yeah,
right.
we're solving for the velocity in terms of what? Like just as a number?
So typically when you're asked to solve for the velocity on an F equals ma question and you're given a bunch of other quantities, we're solving for it in terms of the other quantities.
Yeah.
Okay. So don't we already have square root of RG cosine theta?
Yeah. Okay, so, and then, yeah, I replace v squared, and then I get RG. I'm going to do this on a new line, actually. This is equal to half m RG cosine of theta, right? This is mg times h. So then we have the relationship, these cancel, so like h is equal to half times r times the cosine of theta. Right, okay.
Why is the potential energy equal to the kinetic energy?
Because this is the potential energy that was lost, right? And then this is, we're saying u equals 0 at the height at which the block leaves the sphere.
Okay.
Okay. So we have
Mhm.
h is equal to half r times cosine of theta. But then we also have, if you put it at the center, you can get v squared equals to d times 1 minus cosine theta times g. Then we have h is equal to,
So at that point, h should be 0.
no, we're saying h is like the distance right here.
Okay, got it. All right, got it.
So then 1 minus cosine times d over 2 is equal to h.
Because I think we had that before, right? So then 1/2 times 1 minus, I don't know.
Did we?
I mean, where else would you get 1 minus cosine theta times d over 2 from?
No, right, okay. Right. Actually, scratch that. Oh, I'm sorry, guys. I'm kind of too tired to live solve. So Lewis's suggestion was, if you have u equals to 0 at the center, right, then you have v squared, and then this is d over 2, okay. So you can get v squared is equal to d times 1 minus cosine of theta times g, right? And why is that? Well, d times 1 minus cosine of theta is this bit, right? Yeah. Okay, so actually it's this part, because that's d times cosine of theta, d over 2 times cosine of theta. So okay, yeah, so this part right here is d over 2 times 1 minus cosine of theta, because this is d over 2 times cosine of theta, right? And then, so this is the part that it falls, right? So then the kinetic energy, or the potential energy that's lost, is equal to mg times d over 2, 1 minus cosine theta of g. But this is also equal to half mv squared, right? So then we can cancel out the halves, and then we can cancel out the m. So then we have v squared equals to g d times 1 minus cosine of theta. But then we also want to have like where it slips, right? So then we have v squared is equal to r times g times cosine of theta, right? So we can actually find like what theta is. So we get rid of, so this is d over 2, right? Get rid of g, get rid of d, then we have 1 minus cosine of theta. All right, it's all coming together, equal to half times cosine of theta. Then we have 3 halves cosine of theta equal to 1. Cosine of theta is equal to 2/3, right? So now we know the angle at which it falls. But all we have to do now is put it all in here. We can substitute it back into here, right? So then what this gives us is v squared equals to d times 1 minus 2/3, which is 1/3 times g, right? So then therefore we get v is equal to gd over 3 and the square root of that. Oh, that took me long enough. Okay, thank you, Louis.
Could you explain the mg equals half mv squared part again? You said that the change in the
Well, because energy is conserved, right?
Yeah.
Okay, so you understand why this length over here is equal to d over 2 times 1 minus cosine of theta?
Yeah, the triangle.
Yeah, because of the triangle, right? So then it loses this much gravitational potential energy, right?
Yeah.
But then that
Negative MVA.
because that energy is conserved, it's converted into kinetic energy.
Yeah.
Therefore, we're setting them equal, right? Because energy lost equals energy gained. It's conversion from potential into kinetic energy.
The h isn't the absolute height of it. It's just the difference, the distance it traveled.
Yeah, because it's relative, right?
So it's okay. Got it. Yeah.
Yeah. So then we're saying u equals 0 at the center, and then we're letting the block slide down and convert some of their potential energy to kinetic energy. All right. Cool. Sound good?
Yeah.
We're running a bit short on time. So 17 and 19.
What are we gonna do after?
We're doing frames and relative motion.
Okay.
All right. All right. We'll do more test review during office hours. Jesus. Yeah. I don't know. I'm not in the spirit to live solve today, right now. Anyways, I'm gonna start with frames and relative motion. And this is a topic that we should have covered a long time ago, but I don't know why we just skipped over. But yeah, frames and relative motion. So the first thing we have to consider when we talk about this thing, 17, you find the point at which rotational kinetic energy. Yeah, maybe you can both come to office hours and we can discuss the problems. But frames and relative motion. So what is the frame, right? So what is the frame of reference? So can anyone just like say if they know, like, what is a frame of reference?
It's the frame in which you reference something.
You can't use the words of, you cannot use the words in your definition, or the origin. I wouldn't say that's exactly it.
It's from where you declare the properties of an object. Like if I'm here, then I'm declaring the speed of the object and everything with respect to me.
Yeah, so anchor for position, yeah, the thing you move with. Okay. Yeah, so these are pretty good. So it's like it's the situation in which one observes an object, right? So right, so for example, if you are standing on the side of the road, right, and then I drive by in a car, let's say, and then I was like moving this way, for example, and this is me in the car. So from your point of view, right, if this is you, from your point of view, I am moving to the right, correct? But then and you are just like standing on the ground. But from my point of view in the car, what direction are you moving in? Hello? So so when I'm looking at you, back, no, left or right? Yeah, left, right? So so you looking at me is going right, and then me looking at you is going to the left, right? So then obviously these are both like they can't be true simultaneously from one point of reference, right? But then, it shows that when you look at a situation from different points of reference, then you get like different results, right? So let's just say there's another observer, right? Let's just say Andrew is standing with you on the ground, right? So so when Andrew looks at you, he's gonna perceive you as being still, right? But then when I look at you, I'm gonna perceive you to be moving to the left. Okay, why can't they both be true from one point of reference? They can be, but I'm just making the point that different frames of reference produce like different results based on what frame you're looking at, right? And then, so Andrew looking at you is still, and then me looking at you is moving to the left, right? Okay. Any questions so far? All right. So we're gonna make the distinction of what is an inertial frame and what is a non-inertial frame.
Do we need to know non-inertial mechanics and stuff for the F equals ma?
Well, while it's not necessary, knowing how to switch to certain non-inertial frames are helpful in knowing how to switch to non-inertial frames is helpful in some problems in F equals ma. Like it's more a trick than a topic. Like you know what I'm saying?
Oh, okay. Like com frame.
Yeah. So as you guys might know, some frames of reference might accelerate. So for example, if I'm on a car that's not moving at a constant velocity, then I'm either speeding up or slowing down, right? So let's just say that an observer is in some frame of reference that is speeding up, right? So it's accelerating. However, you being the observer and like not being inherently part of the frame, part of like what's in the frame that makes it accelerate, like you do not want to accelerate, right? Or like if you're actually no, if you're an observer in a frame that's accelerating, an object in the frame does not want to accelerate along with the frame, right? But then since you're looking in the frame of the accelerating thing, then like because frames have no velocity or acceleration with respect to itself, then the consequence is the object that's in the frame is going to be perceived to have an acceleration in the opposite direction, right? So for example, if I am an observer in a car that's accelerating, right, and then you are standing at the side of the road, this is the same example, right? So I wouldn't think that the car is moving because I'm in the car, right? Although you know that the car is moving from looking outside or whatever, like in terms of observers, you wouldn't know that the car is moving because you're in the car. However, it would seem that the person that you're looking at is accelerating this way, right? Because of how you view things. So then therefore any frame, so any object here, even if there's no inherent force applied on the object, it's going to seem like it's going to accelerate in the other direction with the same magnitude as the original frame is being pushed, right? So like this and this, these are kind of like analogies. So any questions so far on this? So it seems like there's a force on everything, but it's really not. It's just you. Yeah, that's correct. Okay. So now that we know that in some frames that are accelerating, things accelerate, well, now we can define what an inertial frame is. So an inertial frame is simply one where when no inherent force is applied to an object, when no inherent force is applied to an object, it does not accelerate with respect to the frame. Okay, so even, and then this can be defined in very practical terms because we all know that like the Earth spins around the sun, right? Therefore, since we're rotating, then every single object on Earth experiences a centripetal force towards the sun, right? Then that means, the frame of the Earth is actually not strictly inertial. However, we can say that it's inertial enough to be like a lab frame because when you put an object on your desk, it's not going to start accelerating for no inherent reason, right? So therefore, we can declare the Earth to be a frame that's inertial enough for like most experiments that you want to do in classical mechanics, right? Okay. And then defined in a similar way, a non-inertial frame is a frame that isn't inertial. Okay. So that means, let's just say you're in a bus, right? And if the bus accelerates, then you're going to lurch backwards. And even though there's no inherent thing that's causing you to like lurch backwards, well, it's just a product of the force of your frame, which is the bus being non-inertial, right? So therefore, you're going to experience that force. And then, so because there's an acceleration that's caused, so then this is experienced as like a quote unquote force, right? So the force that induces the acceleration is called a fictitious force, okay? Because it doesn't really exist, but like you feel it when you're in the frame.
This is like the Coriolis effect, or whatever it's called.
Yeah, so
Centrifugal force.
the Coriolis force is an example of a fictitious force, right? But then there are other more common fictitious forces that you just feel in general. Like for example, like the bus example. Any questions so far about frames of reference?
We gonna learn about relativity?
No,
Oh,
maybe next semester. I don't know, we're still planning out the thing.
I can derive the Lorentz transformations for you guys if you want me to next semester.
Okay. Something important to keep in mind though is that a frame does not necessarily have to be with respect to an object that actually exists, right? So for example, you can just say that you can observe a situation from a frame that moves at 2 meters per second to the right, right? And then you can kind of imagine like, you know, you're moving along with some speck of dust that behaves exactly how you want it to. And then, you know, you can observe a situation that way, and that would be a valid frame of reference. All right. Okay. So now we're going to talk about relative motion. Which is basically a description of motion with respect to two frames, or like two or more frames. So let's start off with an easier example. So let's just say you have like this platform with wheels, and you are on this platform, right? So the platform moves at, I don't know, 5 meters per second. And let's just assume that the platform is long enough so that you don't walk off, right? So then you are walking on the platform at 2 meters per second. Okay. So now let's consider an observer that's on the ground who's not moving. Let's just call this person A and person B, right? Right. So okay, but then let's just say there's another person, person C, who stands still on the cart. All right, person C stands still on the cart. And okay, so how fast is A moving? So one with respect to, or no. So how fast is person B moving? Firstly, with respect to A, and secondly, with respect to C. All right, so yeah, so how fast is B moving with respect to these two observers? You don't need to PM me. All right, so we have 7 and 2. Someone said 7 and 2. So how do you get 7 and 2? It's pretty simple, right? So How do you get 7 and 2? Okay, yeah, so this is just 5 plus 2, and 2 is just equal to 2, right? Because you're on the cart, and yeah. But then to person A, you have to add the velocities of the person and that of the cart because, okay. So how do we better quantify this, right? Because to person A that's on the ground, the cart is a frame of reference, right? This is a frame of reference, or is not a good word? Frame of reference, which travels at 5 meters per second, right? So then, yeah, so C is basically the frame of the cart, right? Because C is standing still with respect to the car. So like whatever C sees is what like whatever C sees is whatever the car sees. So then the car would see the person B moving at 2 meters per second, right? So to generalize this, if I call like velocity of K as the velocity of person K, then we can say that the velocity of B with respect to A, right? Or we just call it VBA. VBA, we define VBA as velocity of B with respect to A is equal to, well, what is this? So this is the velocity of like an intermediary frame, right? And the intermediary frame is that of the car. So then this is equal to the velocity of B. Actually, it's of C with respect to A. But then you add the velocity of the person with respect to the car, right? So then this is equal. So then you add on the velocity of B with respect to the car, which is C, right? So therefore, if I reverse the order of these two, right, we get that V of B with respect to A is equal to the velocity of B with respect to C plus the velocity of C with respect to A. Right, and then, if you look at the letters, right, there's like a nice little transitive property relationship. So then BC plus CA is equal to BA, okay? So any questions so far? All right, I don't see any. I'm gonna move on. Right, so of course, because this works in one dimension, so far we've only used the x-axis, right? Then that means we can actually project this into like up to 3 dimensions. Because if it works horizontally, then it also would work vertically and on the z-axis, right? So then therefore we can actually just turn these into vectors. So VA is equal to V of B with respect to C plus the velocity of C with respect to A. Okay, so then this is just projecting onto 3 dimensions. So my math teacher derivation for the gamma factor for time. Okay. Aren't you in Geo? What are you doing? Kind of like a certain hammer. Anyways, we could also just visualize this purely in terms of vectors. So if I have an object A and an object B and an object C, and at some point in time, they have like certain positions, right? So I'm gonna call it like displacement S. So this is the displacement of B with respect to A. This is the displacement of C with respect to B. And this is the displacement of A with respect to C, right? So then if I want to get to C to A, this is the displacement. So notice that, ooh, wrong arrow. I'm gonna call it this way, right? And this is the displacement of C with respect to A. All right. So notice that from what we know for vector, well, actually, Lewis says y. Why what?
Why Arib showed the derivation for the gamma factor in time
Yeah,
dilation.
that's a good question. All right, let's continue. So the displacement of C with respect to A is equal to the displacement of B with respect to A plus the displacement of C with respect to B, right? So this is very similar already to our thing that we got over here, right? But then now we can take the time derivative on both sides, right? So ddt. So what is the time derivative of position? Or what is the time derivative of displacement? Velocity, good. So then we can write out the same equation that we had before. VCA equals to V, oh God, what did I do? Well, I guess for better ordering, we can do CB and then BA. Yeah, okay, whatever. And then this would be, so then you can see how it goes from C to A, right? Okay. And then similarly, when we take the time derivative, we get VCB plus VBA is equal to VCA. All right, so then it could be moving at some velocity, like this is V, no. So V of C with respect to B is like something, right? And then V of B with respect to A is like something else, right? But then like you add these vectors. Oop, what did I do? You add these vectors together and then you get a new vector, right? And this is the movement of C with respect to A, all right? But then like we don't have to stop here. We can actually go one deeper. ddt on both sides. And we actually get that the acceleration of C with respect to A is equal to C with respect to B plus B with respect to A. And this is as far as we're gonna go for now. We can go like deeper down the DDT chain, but that's not really necessary. Okay, so any questions so far? So just by adding the vectors, we can get motion relative to another object. Okay, questions so far? All right, it's like 5:35. So we will give you a 10-minute break now. Yeah, so if you have any questions, we'll be here, but yeah, see you guys at 5:45.